In this video clip, we are going to talk about remainder theorem. The remainder theorem is going to solve the question I'm written here. The question says that, can one find the remainder without doing the division? If a polynomial p of x, let's say x cubed minus 3x squared plus x plus 5 divided by d of x, which is x minus 2. Here is the question. Is that possible? Find the remainder without doing the division. That sounds impossible. But you know, remainder theorem tells us if the divisor d of x equals x minus 2 under this condition, then we know the degree of d of x is 1 in this situation. Then we know it would be possible for us to find the remainder of any polynomial divided by a polynomial with degree 1. Degree 1 means here the exponent of x is 1. Without doing the division, we may be able to find out the remainder. So that's why remainder theorem sounds like a powerful theorem. Before we do that, we like to recall how we did for the numbers. You see down here we have a 9 divided by 7. The process is we put quotient 1 here. And 1 times 7 is 7. And then dividend 9 minus 7, we have a 2. Then we stop. Because down here, the remainder is less than the divisor 7. So we may then write dividend 9. Dividend 9 equals the divisor times the quotient 1 plus remainder 2. That's the one right here. Okay. So this is what we record for the division about numbers. For the polynomial, is similar. You look at this polynomial x cubed minus 3x squared plus x plus 5. That's a polynomial. Now divided by d of x, which is x minus 2. So you do the long division in this way. Okay. And here you have a divisor, and here you put dividend here. We do is we have a x squared put here. X squared times x is positive x cubed. Now I put negative here, which is opposite. And then x squared times negative 2x, we should get negative 2x squared. But I put opposite because upstairs the polynomial needs to subtract downstairs. So that's why I put opposite sign right here. Okay? It's like here we have what? We have a It's like here we have a subtraction. Even 1 times 7 is positive, but we do subtraction. The same. So we have x cubed cancelled, and then we have a negative 3x squared combined with positive x squared. So we have a negative x squared. Then we need is negative x times positive x. We have a negative x squared here. Again, we do subtraction, so it comes to be positive. And then negative x times negative 2 is positive 2x. We do subtraction, so we have a negative 2x. Those x squared will be cancelled, and positive x, negative 2x, comes out to be negative x. So we have a negative 1 we put right here. Negative 1 times x is negative x, but again, we do subtraction. Here we'll change the sign to positive. And then when you do the operations, negative x, positive x will be cancelled. Take 5 down here, and then you have a negative 5, negative 1 times positive x, you have a negative x, and then again do the subtraction, you have a x. So negative 1 times negative 2, you have a positive 2 here, but you do subtraction. So you have a negative. Eventually, negative x, positive x cancel each other. You have 5 plus negative 2 equal to 3. So you stop. The reason, again, is similar to what we did before. Before is 2 less than 7, we have to stop. Right here is because of what? It's because of this thing right here. Is because the degree of x minus 2 of this divisor, degree is 1, which is greater than the degree of the remainder, because the remainder is a constant. That means the degree of the remainder is 0. So you can stop right here for the division. All right. Okay. Now, then we know, similar to the 9 equals 7 times 1 plus 2, similar to that one, we can rewrite as this expression right here. We can rewrite the p of x, p of x right here. P of x is x cubed minus 3x plus 5 plus x plus 5. D of x is x minus 2. Then we know here we have got what? We have got the quotient. So we then times the quotient x squared minus x minus 1 plus the remainder 3. Similar to the expression we did here. We can do the same thing. Like that. Okay. Here is that after we write p of x, any polynomial, in this way, since the divisor has degree 1, the remainder will be the constant, and we have found this quotient. So, the quotient times the divisor plus the remainder will be the original p of x. You can try it. You can expand x minus 2 times x squared minus x minus 1, and then plus 3, you will get this one. Okay, you will get this one. All right. Now, then you can see if you write P of x in this way, 3 is the remainder. If you plug in 2, substitute 2 for x, what would you get? You replace x with 2. You'll get 2 minus 2 is this one. 2 squared minus 2 minus 1 is the number here, plus 3. The first, this part, is 0 because 2 minus 2. This basically tells us P of 2 is 3. Okay? So you see 0 times 1, because 2 squared minus 2 minus 1 is 1 here. Okay, is 1 here. So basically you have P of 2 equals 3, which is R of x, which is a remainder. So it's possible in this way, you will get the remainder without doing the division. What is the remainder? You got it, probably you still don't know how I actually got it. Is what? Is this. Plug in P of 2, you will get 3, number 3. Okay, you will get number 3. All right. Plug in P of 2, you get number 3, and number 3 will be the remainder. Okay, so that basically tells us that without doing the division, we can actually find the remainder. So you do actually, you plug in is not the 2 you want to plug in here. You actually want to plug in here. 2 cubed minus 3 squared plus 2 plus 5. You should get 3. Okay, because those two are equal. This one and this one are equal. Okay, do you really get 3? Sure thing. 2 cubed is what? Is 8. 3 times 2 squared is that 12? Plus 2 plus 5. That will be 3 for sure. You see, 8 plus 2 is 10, plus 5 is 15, minus 12 is 3. Okay, so this tells us that remainder theorem, with remainder theorem, tells us that if x minus 2 as a divisor, this one as a divisor, to divide this polynomial, 2 it comes from here. Why do you need to plug in 2? 2 comes from here. Okay. If this polynomial with degree 1 is going to divide any polynomial, here the polynomial is special, is degree 3. Here is the degree 3. Then you can get the remainder 3 without doing the division by plugging in this number 2 into P of x into the original one here. Whatever you get, that will be the remainder. Very powerful. Very powerful. Okay, then here is the general what? Here is the general theorem. Remainder theorem. So the remainder theorem says that if a polynomial p of x is divided by x minus c, then the remainder will be what? Then the remainder will be p of c. Okay? That's basically it says, any polynomial p of x, if it's divided by degree of 1 this polynomial, then you plug in this c, not negative c, into p of x. Whatever the value you get, that will be what? Remainder. Yeah, that's the celebration we got to make. Okay. Now, the proof is actually not that hard, the general proof. Okay. So here is the proof I'm going to show you. So, assume the p of x is the one we are given. And here is the divisor. Then we have the quotient. And here is the remainder. So any polynomial p of x can be written in this way. Okay. And here x minus c has degree 1. 1 is from here. Okay. Yeah. And then if we use x minus c as a divisor to divide p of x, we got the quotient q of x by long division with remainder r. Then p of x can be written in this way, p of x. And then we plug in c. We plug in c here. We got this one will be 0 right here. Whatever QC is, 0 times QC, you get 0. And then this whole quantity will be 0 plus R. That's still R. So R, this number is the remainder, which actually equals P of C. Okay? So this basically tells us that for the remainder theorem, we do not have to do the division to find out remainder, R. What we like to do is plug in C, this constant, into this polynomial, which is not factored. Okay, and then we may get the remainder. All right? Okay, I'll see you next time.